All right, looks like it's working. PF1 video 6, and let me pull up my folder here and go and open my little drawing tool real quick and make a suggestion as we start today. Now typing in programs from scratch here in class. So let me go here. And this isn't too bad of a place, actually. I might even just leave some of that there. We'll see. I don't know. Oh, what the heck. We'll just get rid of it all and start from scratch. Doot, 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 doot. Maybe a little more. Okay, so we are going to, today, and I'm going to say every day to follow, we're going to be typing in programs during class. So I'll be typing them in from scratch, and you guys can kind of do the same then, and in your seats, and be typing in lecture notes and so on. Then also, and I mentioned before, if it is the case that you fall behind, you get some unknown weird error that's causing your program to not compile or run right or whatever, just raise your hand and I'll copy mine down to a common place where you can copy it to your directory, and just like that you'll be caught up. And and in fact, if by any chance, if you're a slower typer than I am, and you might perhaps just concentrate maybe on just your notes, and then watch the videos later on to type in the code, or just ask me to copy them down to make them available to you, kind of whatever there. But hey, speaking of the videos, I did want to mention that when I post those videos on Google Drive, I do go ahead and require that you be logged into your AmarilloCollege.com account. I don't remember if I've mentioned it to this class or not, but anyway, if you're wanting to watch those videos, you go to Blackboard, and there's the links. But anyway, I guess the good news is if you're logged into Blackboard, you're probably logged into your AmarilloCollege.com account. But anyway, so then you follow the link then. But if you're not logged into your AmarilloCollege.com account using the same browser, you'll get a permission denied error on that. But anyway, so what I'm going to do every day is just log in. And just right here in my home directory, I'm going to then start typing in my sample programs. And then, well, either at the end of class or very likely just at the beginning of the next class, I'll log in and look and see that I have a bunch of stuff there from the previous class, and I'm going to wipe it all out. I'm going to remove it. But of course, you guys don't want to do that. You'll want to have those to refer back to and so on, all your example programs. But kind of thinking ahead, if you were to follow my example and put all of your sample programs in your home directory, well, then you're going to come back in PF2 and do the exact same thing. It's really going to get kind of messy in there, And I used to try to think of, creative, descriptive file names for what is this program here doing, and try to give a name that is a good name based on what that program tries to solve. But in the end, I just kind of threw in the towel. And what I'm going to do here today, the first program we're going to write, and I'm just going to name the programs after whatever video this is. I announced at the beginning of the class this is video 6. So we're going to have vid6.java. If I create a second program, it's going to be vid6b.java. So we're going to organize it by day, in other words, or by video. All right. And so we recognize that if we are typing in vid6.java here in PF1 today, it's very likely we're going to come back in PF2 and also have a vid6.java. So you don't want everything in the same directory. All right. So it'd be okay now, but you'd have to clean it up eventually. So what I might suggest, all right, so underneath your home directory, you have a PF1 directory, of course. You guys are well aware of that by this point. Hey, that was very weird. What happened there? Okay, Control Z. That was very strange. I don't know how I managed to do that. Anyway, and so of course you're going to have your lab 1 and so on. Lab 1. ... You're going to have all of those, but you can create other directories here underneath PF1. So I would suggest that you come underneath your PF1 directory and create a directory of whatever the heck name you want. You call it notes or samples or examples or lecture or, whatever the heck you want. I don't know, samples, lecture. And then you could put your files underneath here if you want. Or you could even organize it by day if you want. I mean, if, kind of just whatever your preference is, but kind of give it some thought now, and you might kind of refine that in the next few days to follow or whatever before you get too far down the line and have a lot of cleanup to do if you want to reorg. If you wanted to have a directory called, for instance, vid6, and then, because on many days we'll have at least 1, maybe 2, 3, sometimes 4 or 5 programs, and then you could have, come back the next class period, have vid7 or just kind of whatever. But anyway, I would suggest that you, one way or the other, put your sample programs underneath lecture examples, samples, whatever, notes, something like that. Name that whatever you want. You can, no problem there for you to have an extra directory into your PF1. So I would encourage you to do something like that. Okay, so we've completed your lab 1, and that did a good job with that, but you just kind of typed it in. Now, we kind of hit the highlights. We went through and I described a number of things about it, but of course there's lots of little details that you need to thoroughly understand, not just have some vague idea what they're connected to or whatever. So today's the day then. We're going to back up. We're going to start from scratch, typing in a program just from scratch, and we're going to write the smallest little program that will just compile. And in fact, it'll compile, but believe it or not, it won't even run. But still, we're going to learn all about that little program, and then we're going to add another piece and add another piece and add another piece. We're going to cover these things in much greater detail, where by the end of, certainly by the end of the next handful of lessons, there'll be little left then, by the time we get to the midterm, certainly. So there'll be little left in your Lab 1 that you won't understand pretty thoroughly. All right, so that being the case, let me get my login opened up here then. And oh, what the heck, while I'm at it, we'll get this ready to go for notes. All right. So vid6. All right, there's that. And okay, so let's see here, and I think we're ready to go. And in fact, I got a little bit of cleaning up to do from last time when we learned VI. Remove my first file, didn't need that anymore. Remove lab2.java, and if there's a class file, remove it at the same time. And remove vid whatever here that are written in C++. And there we go. That's about as good as it gets. All right. But again, I don't recommend that you guys do that you wipe these files out after you type them in. But anyway, I'm just keeping my home directory clean. Okay, how about VI vid6.java? So again, we're going to start from the smallest little program that will just compile. All right, so we're going to start out with then, go into insert mode with an I. And how about public class? And I'm going to go and type vid6 as such. We may end up changing that and coming back to it here in just a second. And then on the next line, an open curly brace, and then a closed curly brace. And then that is it. So wow, there you go. That's the smallest little Java program that will compile. And as we mentioned then, this here is called the class header. Notice it contains the word class. This word public, it's an access specifier. We're going to talk more about it later, right after the midterm. So anyway, so we're going to kind of gloss over this for now, but we'll come back and we're going to talk about every darn bit of this, certainly this semester, and much of it by the midterm. But anyway, so it has the word class. And then following the word class is the name of the class that we're wanting to create here. So we're working on a class called vid6. And so anyway, then after our class header, we have an open curly brace and a closed curly brace. This is the body, if you will. This block of code is connected to our class. And it doesn't have any code in it. But again, this is the smallest little program that will compile. And we're going to show how it will compile. We can make some changes to it. It won't compile, but anyway, just to introduce and show you more about errors and so on. So what I like to do when I get out of VI, you don't have to. It's funny, sometimes students think this is a necessary part of the process. But in case you were still typing and then I exited the editor, well, the first thing I always do is just cat it. So it displays it on the screen. So then you have one more chance here then to catch up with me, while I'm kind of moving on to the compilation process here. I'm going to do just that. So I've catted it. How about Java C, vid6.java? Hey, there we go. And it did compile. And as a result of it compiling, now when I list all, so I'm using a wild card here. This asterisk is a wild card, or a star we might call it. So ls minus l on everything that starts with vid6. So hey, there you go. I've got vid6.java, vid6.class. Again, in this particular case, it looks like they have the same modification time, but we know that the class file is a few seconds newer, because after I got out of VI, then I compiled it, and the class file was created at that point. So it did compile. The program did compile. How's that for a simple little program? One line of code, plus the curly braces there, then for a total of 3 lines of text. And no big deal. And just for the heck of it, I'm going to either change the class name or the file name, one or the other. Oh, I don't know. I guess I'll change the class name. So I'm going to go back in to VI, and I'm going to come over here and change the uppercase V to a lowercase v. Hey, speaking of that, here's yet another VI command. If you have your VI cheat sheet handy there, kind of a neat little thing. I just need to change uppercase to lowercase here in this case. And anyway, there's a VI command that will do just that. So put my cursor there, for instance, and notice if I hold down the shift and hit the tilde key, that's the shift of the back tick, which is the upper left key underneath the escape key. And check this out when I hit the tilde. Tilde is a command to VI. Tilde, 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 tilde. If I'm tildeing across, it changes uppercase to lowercase and lowercase to uppercase. Anyway, pretty cool. And also, VI does have multi-level undo, so I'm going to just U to undo that. Or in fact, I could have just gone over to the beginning and done tilde again just to kind of reverse everything back the way it was. Or there's another couple of commands, U for undo, and it is a multi-level undo. And anyway, the tilde can be kind of handy. And in fact, here's yet another command in VI. So I want to get rid of the uppercase V and replace it with a lowercase v. So I could X to delete it, and then I for insert mode, and then type in the lowercase v, and that would work. But anyway, you can also replace things. So if I, capital R will just allow me to start overriding, but lowercase r, this isn't on your cheat sheet, but anyway, lowercase r allows you to replace just one character. So I'm in command mode. I'm going to type an R, and now it's waiting for this new character. I'll type a V, and there you go. So that's kind of the easiest way to replace a single character, is just to type the command R, followed by that new character, and it leaves you in command mode. So that will work. So I just changed the class name to a lowercase vid6. So I'm going to get out of VI, and I'm going to cat again, and then compile, or well, try to compile. And when I try to compile, oh, got a compiler error. So it looked at the code, and I saw that on my class header there, I had a class called vid6. And as a result, this class header should be declared inside a file named vid6.java with a lowercase v on the file name. So in other words, the Java compiler expects that class name, which is specified inside the file, to be the same thing as the file name. In fact, just look right here at this command, cat uppercase vid6.java, but the class name inside is lowercase, and Java is case sensitive just like Unix is. And anyway, the compiler says, no. A class called lowercase vid6 need to be in a file called lowercase vid6. So I could fix this one of two ways. I could change the file name, or I could change the class name. Now we're going to show you some rules on how you can and should name variables and methods and classes. We're going to show those to you, well, the next class period. But for now, I'll just go ahead and give you a sneak peek. One of those rules is that class names should, the compiler doesn't enforce it, but class names should start with a capital letter. Well, we had that earlier, and we had that earlier until I just went in and changed it. But anyway, class names should start with a capital letter. Now this class name does not start with a capital letter, and the compiler lets that slide. It's a convention instead of a rule. But if, in terms of which one to change the file name or change the class name because they need to agree, well, we'll change the class name. So back in we go. Back into VI. Come over here. And again, we could just say R, then capital V to replace the lowercase v with an uppercase V, or just hit that tilde again. Would be fine too. All right, so now when we cat the file name is vid6 with a capital V, and then the class name is vid6 with a capital V. And now when we compile, hey, there you go, it did compile. So we should have new modification times on both of those, and we do. And now it's just a matter of running it, and I haven't run it yet. I haven't tried to run it. And well, I did mention earlier, this is the smallest Java program that will compile. But as a matter of fact, it is so small, it doesn't quite have all of the necessary ingredients. It's kind of strange to actually run. So what's going to happen when I type Java vid6? Remember, when you're executing the program, you don't put .java, you don't specify .class. It's just you're specifying the class name, and the class name comes from the class header. The class name is just vid6. So when I type this command here, so Java is the name of the program that that contains the Java runtime environment, that virtual machine. So it's going to launch. Then it's going to see that we specified vid6 there on the command line, so it's going to look in my directory for a file called vid6.class. It's going to see it. It's going to read it into memory, and then it's going to look for the main method. It's going to read it into memory, then it's going to look inside it trying to find the main method, because execution starts at the main method. And so although this program did compile, so this isn't a compiler error, this is a runtime error. So anyway, that's an interesting little lesson, I guess, for a new programmer, is you can get errors when you try to compile a program, like right here. And you can get errors when you try to run your program, like we have right here. And how do we know it's a compiler error versus a runtime? Well, look at the command. I'm compiling up here. Down here, I'm trying to run the program, and I got an error. The main method is not found in the class called vid6. And it even tells you, please define the main method as. It specifies right here the syntax for our main method header. But anyway, so isn't that interesting? You can have a class file that will compile, but that doesn't have a main method, and as a result, it won't run. That'll all kind of make sense, about after midterm when we start creating programs with multiple classes. But for right now, it seems kind of silly, I guess, to have a program that will compile and not run. So let's fix that. So back into VI we go. All right, so inside of our the block of code that's connected to our class, I'm going to go into insert mode, indent 4 spaces, and here is our main method header. We'll type this every day multiple times. You guys will memorize it no time at all. Public static void main, all lowercase, and then in parentheses string args, string with a capital S, and then followed by args, A-R-G-S, with a pair of square brackets at the end of args. Oops, that's not square brackets. There we have square brackets. And then a parentheses to match that up. Again, the parentheses and the curly braces and the square brackets all need to match up as pairs. And then underneath that, indent by 4 and an open curly brace, indent by 4 again and a closed curly brace, and ta-da! We have implemented our main method. Now let's go back to our notes here real quick, just to stick something in there, I guess. All right. Note that when we run our Java programs, all right, and then we'll do this. Execution starts at main. All right, that's kind of that. We're going to tell you what we're going to do here on that. I'm going to go back to the beginning and make that a pro tip, if you will. Just something. You know, there's a number of little phrases that kind of need to stick with you, that are kind of part of the terminology of any number of study of technical areas and so on. This is kind of one thing to remember is, oh yeah, execution starts at main. We could have written a method with different names in there, but anyway, in order for Java to know which method to call once we start writing programs with multiple methods, it's going to look for a particular one called main. And there's some details you have to get about it right also, but we'll talk about those later. Execution starts at main. All right, so there's that. All right, and back to our code we go. And so now I think we're done here. We've added a main method. Now, you know, the main method, this is its body down here. You know, once again, this is the main method header. We went over that, or, you know, mentioned that briefly last class periods. This is the main method header. And then this is the body that is connected to the main method. And the body doesn't have anything in there, just the little kind of like a fence post or something here. I guess you just mark the beginning and the ending of it, but anyway, there's nothing in that body. So again, this is the smallest program that will compile, oh yes, and it will actually run. All right, so we will, for good luck here, we'll cat and compile. All right, it did compile, and then we're going to run it, and unlike last time, it will actually run. So it's going to, again, when we type Java vid6, it's going to look in my current directory for vid6.class. It's going to find it. It's going to load it into memory. Then it's going to look inside of it and look for that main method. Aha! It does have a main method. And then it's going to execute the main method, and there's not any code inside of it, so we won't see any output or anything very dramatic, but no runtime errors. So ta-da! Our program ran and did, well, nothing that we can see here. It just was loaded into memory. The main method was executed, and the main method was essentially empty. So we can't see any real results here. So that's kind of not very satisfying to have a program run that doesn't generate any output, you know. And so traditionally, whether you're a new programmer or not, even if you're, have a fair amount of experience behind you, but perhaps you're working with a new language, and I certainly remember this being the case, that I needed to implement some code in a language I wasn't very familiar with, or maybe it was a development environment that I wasn't very familiar with. Maybe I knew the language, but I'm using different tools or whatever. And I have before got a program that I copied over from some other environment and compiled it up and tried to execute the thing, and I couldn't get any output out of it. And I was wondering, well, what the heck is going on here? Is it my program, or is it something about the development environment that I don't understand? What's going on? And if the program I copied over was very complicated, then I was perhaps a little less sure that I hadn't somehow introduced an error there. So then in order to debug it, what you want to do is get the smallest, simplest little program possible that will just generate a little bit of output just so you can try to compile and run it. And the smaller and simpler a program is, of course, the greater confidence you can have that you don't have any errors in it. So, and that's just a very common thing, again, for new programmers, or maybe for experienced programmers that are working in a new environment or a new language or whatever. Very common. Hey, let's see if I could just put together the simplest little program possible. Will it just come up and display some silly little message just so I can see that it ran? This looks pretty good. It compiled and it ran, but I didn't see any output. A little bit of output of, some output of my choice would be kind of good. So traditionally, in situations like that, programmers write a program that is called, does anybody know? It has kind of a historical explanation. So Ken Thompson and Dennis Ritchie, they worked at AT&T Bell Labs, and there's another one of their coworkers there. His name was Brian Kernighan, and he ended up tagging up with Dennis Ritchie, and they wrote the authoritative C programmer's essentially Bible. It wasn't called that, but if we go to Google, and if I type K and R, oh, I can't believe it. It actually wasn't the first choice. Anyway, K and R C. This is Kernighan, this Brian Kernighan guy I just mentioned. And then the R is Dennis R for Ritchie. Anyway, Kernighan and Ritchie, they sat down together then when they were working at AT&T Bell Labs, and they wrote the authoritative book on the C programming language. If we go to images here, great big, there we go. This is an early version, it looks like here. Gosh, this here's really even kind of faded out. So Brian Kernighan and Dennis Ritchie. Anyway, I think Brian Kernighan was the first programmer to actually name this program, and then programmers ever since then, that was 60 years ago or whatever, have been kind of doing the same thing. He wrote a program for this exact same purpose, just to compile, run, and generate a little bit of output. And what he did in his program, and then programs similar to this have been named similarly. Let's write one more line of code. How about system with a capital S .out.println. Notice how println is spelled and pronounced. We call that println. The word print looks good. Line only has an L at an N. Anyway, the name of this program unofficially is going to be called Hello World. All right, so Brian Kernighan is the programmer back in the early 70s, credited with having written the first Hello World program. And he showed his friends, I guess. He was so proud of it. And anyway, for whatever reason, it stuck. We all do silly little things, but his silly little Hello World program somehow managed to make it into the programming pop culture, I guess, or vocabulary. So it's a little program that's not going to do much, not very much, very useful, but when the program runs, it is going to print. Remember we talked before that, well, print doesn't mean on a printer, it just means to display it to the screen, to the terminal, if you will. And it's going to display the phrase, hello world. That's what Brian Kernighan used this first time, and millions of programmers have used it ever since. So we can get a little bit of output out of the program just to see that, sure enough, it compiled, ran, and it produced some meaningful output. All right, so how about we cat for good luck and compile and run. There we go. Hey, looky there. So we get our hello world. And so we're pretty confident there that that's good. So what we might do, just for the heck of it, when I learned programming all those years ago, and I'm sure at some point I wrote my first Hello World program, and did I ever hang on to that darn thing? No, it's lost in the ether, I guess. I guess back in the day it might have been a little harder for me to get access to an electronic copy of that. And of course I could have copied and pasted from a terminal emulator or something like you guys did. But anyway, I don't have any of the code that I wrote when I was a student, but it's not unusual at all for my students after having gone through PF1, 2, and 3, and they definitely learned some things, and especially 2 and 3, some pretty neat little programming tricks and so on. That'd be kind of nice to bring with you, because it absolutely is the case that whether we're talking about programs you wrote when you were a student or early years as a programmer, you will, for the rest of your career, find yourself sometimes with a little problem you're working on. You say, you know, oh yeah, this little piece of it, that's kind of like that thing I did all those years ago. Let me dig that thing up and I'll copy and paste and tweak it and so on, kind of use it as a starting point. So anyway, having access to your code years later. So I'm going to give you the opportunity, just for grins, I guess, to actually have the very first program that you perhaps ever wrote, and it was a Hello World program written in Java. So we're going to leave that unmolested here, if you will, and we're going to then go on to vid6b.java, where we'll do some things that are similar to that. So tell you what we'll do, and this is not uncommon also. I'm going to copy vid6.java to vid6b.java, and then we're going to start working on vid6b. So I'm going to cat vid6b.java. Now I'm going to compile vid6b.java. So my bonus question for you guys is, will this program compile? Java C vid6b.java. Would you guess it will compile? It is a copy of a program that just compiled right here. It just compiled. And then I made a copy of it. And then I'm going to try to compile it again. Anyway, the tricky answer is no, it won't compile. And the reason for that is we're going to get an error message that we saw 10 minutes ago. Does anybody know what the reason is before I hit enter here? The class name and the file name. Exactly right. Very, very good, Zach. Yeah, the class name and the file name have to agree. So when I copied vid6.java to vid6b, I got a brand new file called vid6b. And anyway, vid6b, for it to compile, it needs to have a class inside it called vid6b. I don't have a b on the end of that because I didn't edit the contents. I just copied it over. So here we go. You know, we need to fix this one of two ways. I either need to change the file name. Well, I've already got a vid6.java. I want to leave it there. That's your pristine copy of your very first Hello World program, probably ever, and certainly so in Java. Anyway, so we're going to leave that there, and I want to start working on vid6b. So, well, we'll change the class name. So I need to go into VI and edit vid6b. So VI vid6b.java. All right. Hey, so capital A puts you in insert mode at the end of the line there. Put a B on the end of it, and there you go. Escape, capital ZZ to get out of VI. So once again, we'll cat vid6b.java. Java C vid6b.java. And then I'll take Java just to get my command history built up, because then I can just arrow through. I'm going to go ahead and do Java vid6b, and it did run. So this is kind of a good idea, you know, to get your command history. VI, cat, Java C, Java, and then you just arrow back through those. Because every once in a while you might make a mistake. I'll probably do it in class at some point, where I'll forget to get my command history built up. And so I'll be editing vid6b, and then I'll use my arrows, and I'll walk back through, and I'll actually execute vid6, the previous program. And then we're standing here, why the heck how come the changes I put in there aren't reflected? Oh yeah, oops, I'm actually executing the wrong program because I was lazy and I just walked through my command history, but the program I tried to execute wasn't the most recent one that I'm working on. So I haven't made any changes to this file at all, other than just the class name. Anyway, to be clear, that's not a bad idea for multiple reasons. Get your command history set up, so go ahead and edit and cat and compile and run, even though you've made none or basically no changes at all. It's a good idea for your command history. And one other thing is, there have been times where I've copied over a program and then jumped in and started slicing and dicing and butchering it up and so on. And then I have some weird problem. I can't get the dadgum thing to compile or run or whatever. I have some kind of weird problems. And it makes me think, you know, I wonder if the problem, I didn't do very much or whatever. You know, I wonder if the problem might have actually been from the source code I made a copy of. And then I'm not sure. So it's a good idea, if you're using some program as a starting point, copy it over, do all the stuff for your command history, and also to make sure it will compile and run, and now you have a known starting point. A known starting point. I know this thing works, so if I go to doctoring it up and then all of a sudden it doesn't work, well, it's something I did in the last few minutes. So anyway, so there's that. So let's play around. Oh, well, I'll tell you what, let's explain what this is, and we're going to just play around a little bit with this existing program. So I tried to hit enter a couple of times, and I fat fingered it, and I hit the backslash. The backslash is the key right above the enter key. And now what the heck? What's going on here? This might be kind of confusing. You know, this right here, That's called my prompt string. It's prompting me. It's asking me to type in a command, kind of like on your lab 1. Enter a number, -1 to quit. We're prompting the user. So the prompt string is on Linux, built in right out of the box. Inside of square brackets, it has your username, @ and then the server name, and then it's telling me I'm in my home directory. That's what the little tilde is for. And then the $ is the last part of the little prompt. But anyway, I accidentally hit the \. What the heck is that? Now I have this greater than sign down here. Well, this is the secondary prompt string. This is the primary prompt string. This is the secondary. So what does that even mean? Tell you what, I'm going to hit Control-C here. That's one way you can get out of it. Why is that? Well, I might be typing in some big, long command, and I could just let it wrap around on its own, but I could also continue it on the next line. So check this out. If I type ls and then \, that's telling bash, hey, I'm going to continue typing this command on the next line. And then space -L. So I type the ls on one line and -L on the other. But anyway, because of the \, it just says this command is going to be continued on the next line. And then when I hit enter, look at there, I get ls -L. Kind of strange, you don't really have to put that \. You could just let it kind of wrap around on its own. But if you want, you could explicitly break a command and then finish it on the next line by hitting that \. there. But if you ever do it accidentally like I did just up here, hit Control-C just to get out of it. It's fine. Okay, so let's experiment a little bit with vid6b here and just play around with our print line statement just as a little exercise here real quick. So back in we go. There's that. And okay, tell you what let's do. Let's print hello world, but let's use 2 print statements instead of 1, just for the heck of it. So we're going to practice with copy and paste as we go then. So I'm going to do a YY and a P. And I'm going to leave hello on the first print statement and then world on the second print statement. All right, as such, and then come down here and as such. And this would be kind of okay. So this is going to print hello world. This is going to print hello on one line and world on the other, which is fine. So let's do that. And then we're going to try to put it back where it prints just like it did earlier. So I'm going to cat and compile and run. All right, so we get hello world, but anyway, the 1 word per line instead of the 2 words on the one line. So I want to make it print on one line. So we're just going to show you a variation of the print line method. So back in we go. And now what I'm going to do is I'm going to change the first print line to just print. So what print does is it displays what you tell it to and it leaves the cursor there. It leaves the cursor there. So for instance, on your lab 1, when you're printing that prompt string, enter a number, -1 to quit. That was with a print, and you left the cursor there because that kind of makes sense because you want to have the user type in the number right at the end of the prompt string. Just like we're typing in our commands, they're right at the end of the prompt string that bash gives us. So it's going to print hello, it's going to leave the cursor there, and then we're going to print world right where we left off, right at the end of hello. Now, in fact, they're going to be crammed right up against each other because there's no space in between them yet, but we'll fix that next. So we get out of VI, we'll cat and compile and run. Hey, there we go. So now we have hello world all on one line. So, oh yeah, now we recognize, oh yeah, I need to put a space somewhere. So the fix is either put a space after hello or before world, whichever makes sense to you. So we'll do just that. All right, we'll come over here. There we go, put a space before world. And one more time for a cat compile and run. All right, hey, there we go. So 2 print statements generate 1 line of output. So in doing so, we introduced print line, which prints what you tell it, and then prints a new line character, which brings the cursor back to the beginning of the next line. And print, on the other hand, will display what you tell it to and leave the cursor sitting there. And then whatever is displayed next will just get tacked onto the end. So after hello, the cursor is left sitting right here. And then we type space world, and there you go. Now, one thing that could be kind of ugly is what if we were to change this next print statement to print, from print line to print? And we'll do that. And the results are going to be kind of ugly. So it's going to print hello leave the cursor there. Print space world and leave the cursor there. And it's going to look weird then when we run the darn thing. We'll cat and compile and run. And at first glance, you look, where the heck did the output go? Oh yeah, it squeezed it over here. So it printed hello, left the cursor there. Printed space world, left the cursor there. Then the program exited, and the cursor was still there. So that was kind of our fault. And then bash does what it normally does, which is to print this prompt string for us then. But since our output was squeezed in before that, it doesn't look very good. So anyway, so it wasn't that the system did something wrong or hiccuped or whatever. It's that our program left the cursor hanging out there at the end of the line. So back in we go. We'll change this second print to print line. That'll fix that back up. Then we'll do kind of the opposite real quick. So we'll cat for good luck, just to make sure it's still fine. Compile and run. Okay. So there we had two print statements that generated one line of output. Similarly, we could have one print statement that generates more than one line of output. So we'll do that next. All right, so into VI we go, and we'll come down here. And you know, one thing we could do also is system.out.println. Look at that there. So that's a little different one. That says print absolutely nothing. But when you're done, then bring the cursor back to the beginning of the next line. So in other words, it's going to print a blank line or print an empty line. Because both in our program and then also in the output of the program, having some white space in there is helpful. Hey, speaking of that, just for grins, let me show you something here real quick. Okay. Do I want to do it? Well, I'll tell you, we'll do it to this program after we're finished. So I need to remember to do this. All right. In fact, let me leave myself a note here. All right. Oh, yes. Okay. So now we've printed a blank line, and then we'll come down here and system.out.println. Okay. So here's something kind of interesting. What if you wanted to print as part of your string literal, you wanted to print a new line character, if you will. So let's type, I'll tell you what we'll do, we'll just play with hello world again. I'm going to type hello, and then hit a enter key, and then world. So I typed hello, and then the enter key, and then world. So when I print that, is it going to print hello, and then the blank line, bring the cursor back to the beginning, and then print world? When I hit that enter key here, it brought the cursor back to the beginning of the line when I'm editing the program. Is it going to bring the cursor back to the beginning of the line when I'm running the program? Or in fact, will the program even compile? Let's look and see. So we will cat and compile, or well, try to compile. Hey, this is a good little error. I like this, because I have basically one mistake in my program, and it caused 3 syntax errors. So, once again, fix the first error. The others probably come from the first one, or very likely do. I have an unclosed string literal. So, no, it doesn't work to have a string literal that starts on one line and goes down through to the next line there. So it doesn't like that. So we just need to bring those 2 lines together. So back into VI we go. All right. So here's yet another VI command. How can I join these lines together? In Notepad, I'd put my cursor over there and hit the backspace key or something like that. This is another VI command that you don't have on your cheat sheet. If I put my cursor anywhere on this line and I type a capital J for join this line with the one below it. Hey, there you go. So capital J joined those 2 lines together, and that looks pretty good. So that will compile now. But what we wanted was after the word hello, I wanted a new line character. But if I just come over here in insert mode and hit the enter key, it's not going to give that to me. So how can I insert a new line into a string literal? Here it is. See the \n, this little 2-character sequence is how we can embed a new line into our string literal. So \n, where n stands for new line. So now it's going to print hello, and then it's going to print the new line character, if you will. It's going to bring the cursor to the beginning of the next line, and then it's going to print world. And in fact, oh, just for grins, let's come to the beginning of this line and do a backslash in there. And we'll put an extra backslash in at the end as such. And I'm going to do one more print statement then. I'm just going to print the end. So we can see that we have spaces before and after and so on, this weird hello world there in the middle. Like all good stories, they should end with the end as such. All right. See some students carefully looking up here. So backslash n appears as a pair here in front of hello. Backslash n appears as a pair here between hello and world. And backslash n appears at the end of world inside of our string literal. So this print line is going to print a blank line. The backslash n is going to give us a second blank line. So we're going to say hello world on one line. Then there's going to appear to be two blank lines, and then hello, and then on the next line world, and then an extra new line there. So we'll have a blank line and then the end. Let's see if that works out like we think. We will cat and compile. And eventually here, there we go, run. So sure enough, print line prints one blank line. Backslash n gives us another blank line. So we see, sure enough, there are two blank lines here. And then after we print hello, this embedded new line here then brings the cursor back to the beginning of the next line. So world, it displays at the beginning of the next line. And then after we print world, hey, we'll squeeze in another blank line there. Then sure enough, we see that here. And it leaves the cursor then sitting right where the end prints next. So anyway, so you can have multiple print statements generate one line of output, or good grief, you can have one print statement generate many lines of output as desired then. All right, not too big of a deal. And anyway, that's kind of it for just introducing print and print line. We can, of course, print variables and so on. We'll start doing that soon. But all that we've done so far is just printing out string constants, are also called string literals. All these things here in between double quotes. Not too big of a deal. Tell you what, let's do. This is going to be a little bit of a shorter day, so we're probably about halfway through then, even though it's only 45 minutes in. But let's go ahead and take a break. We'll come back. We're going to kind of switch gears then and start talking about variables, which are very critical then for us to get introduced here pretty quick. So let's take 5 minutes. So we're back, and per request, I'm going to log out and log back in, get a slightly bigger font on putty here then. But hey, again, I want to say good job, you guys. I'm kind of surprised to see it. That we have eight rows of chairs here then, or 8 rows of computer terminals and so on. And on 5 of the 8, people were sitting there talking. So I think that's a record in the last many years. So that's pretty good. Because it's pretty common for me to walk into a group of students, full classroom, not a word's being said. Everybody's doing this, of course, you know. So very good. All right. There's hope for humanity. Okay, there's that. And does that look a little better? Yes. Okay. So we got that going. Oh, yes. So we're going to kind of change gears then. We're going to kind of change gears. And, okay, get rid of this. And let me bring up. Oh, yes. Okay, trying to think of where to start. And we're going to go here. Okay. So we're going to talk about some integer data types and the largest number of values or discrete values that can be represented with each of them. And I remember having a vague understanding years ago about that until, anyway, the day came when I sat down and actually kind of learned in greater detail. But it's kind of a nice thing to understand if you have an integer data type of, this would be unusual, but 4 bits versus 8 bits versus 16 bits and so on. Well, what exactly does that mean? I mean, we all know that the more bits, the better, and I kind of remember having that vague understanding that more bits allows you to represent larger quantities and so on. But it'd be nice if we could understand it more thoroughly, and so we're going to kind of do that today. We're going to come back next class period, and we're going to start talking in detail about declaring variables and the rules for that, and the rules for naming our variables and our methods and so on that we talked about earlier. And also then what data types do we have available to us and the differences between them and exactly kind of what that means. So we're going to kind of set the stage for that, I guess, then today. So I'm going to draw a little picture and tell us a little story here that will kind of help you understand the quantities of bits and bytes and what exactly they mean and so on. So I'm going to do a little editing here. And I'm going to draw a little box. Okay, it's going to look like a little rectangle. All right, as such, that looks pretty good. And then come over here, and then get my little green brush here so I can draw in. Well, it's springtime, I guess, and anyway, the grass is growing here. I guess that's what this is. All right, so this is grass. We need a little weed eating here. And this, in fact, is the business building. This is the building that we're in right now. And this is the view of this building from across the park that direction over there. So Memorial Park is to our south. And so we can see the back side of the business building. It's 4 stories tall. We're towards the west hand end, so the gym is over here. You know, Parcells Hall is over here. So we're towards the west hand side. So we're like the second to the last room here on this hallway on the 3rd floor. So in other words, this right here, that is our window. Actually, we got 2 windows. We're going to kind of simplify things. So that's our little window. And so I'm going to tell a little silly story again, just to kind of explain the concepts of bits and bytes and how many discrete values can be represented in a certain number of bits and so on. All right, so my silly little story is that tonight you guys are going to meet up in the park over there at 10 o'clock, something else like that. And I'm going to be here in our classroom, and at precisely 10 o'clock we'll synchronize our bat watches, I guess, beforehand. And exactly at 10 o'clock I'm either going to turn, this will be dark by that point, of course, I'm either going to turn this light on or off to convey some message to you guys. So this little window here represents 1 bit, a bit. So we've heard of bits and bytes and so on, very likely. So I guess question number 1, what exactly is a bit? So let's go back to our notes then for some definitions, I guess. Memory definitions. Memory, all right. So a bit, does anybody know what a bit stands for? It's kind of short for 2 words kind of crammed together. Binary digit. So what's binary mean? I'm sure you've heard the term binary. And it kind of has a little different meaning depending on the context and so on. So binary. So binary often refers to base 2. Base 2. So there's some more terms that we can talk about. Let's talk about numeric bases or number bases. All right. So for some reason that I don't really understand at all, I say that jokingly as I hold up my 2 hands here and look at the 10 fingers that I have. For some reason, we're used to working in a decimal system. Decimal is going to be base 10. And the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 digits, and they are 0 through 9. All right. So binary, so we're kind of explaining something that we talked about earlier. So binary is going to be, base 2. So the digits, we'll line these up just because it makes me happy to do so. There we go. So the digits for base 2, man, not many, 0 and 1. So you guys, I'm sure, of course, recognize, you've heard that, oh yes, computers represent everything as a bunch of zeros and ones. In other words, computers function in the binary world, if you will. So just 2 digits, 0 and 1. So a binary digit is a base 2 digit, all right? So that's what a bit is. So bit is short for binary digit. So back to our picture. So you're going to come here at night, and our little window, may be kind of blacked out or not, And precisely at 10 o'clock, I'm either going to turn the light on or off. So we can think of this window as a single binary digit. Because that window is going to show the light status of this room, and the light is either going to be on or off. So binary information, a lot of times, it can store information that can be described as either on or off, or yes or no, or oh yeah, true or false. So binary, there's just 2 possibilities, such as true or false, yes or no, on or off. So certainly our little window here would be a perfect little binary digit. So the secret code is at 10 o'clock, you guys are going to meet up in the park. And if the light is on at 10 o'clock, that means I'm treating everybody to Taco Bell. All right? And we'll meet at Taco Bell down the street there at 10:05, and I'm buying burritos and Cokes for everybody, kind of a thing. So it can store And it can also kind of convey, if you will, a single bit worth of information. That's not much. It's the answer to a single yes, no, on, off, true, false kind of question. In this case, the question that it can store is, hey, is old man Usnick buying Taco Bell for everybody? And the status of that one light, that one bit, can answer that question. It's not much of a question, not much of an answer, but you're very limited with a single bit. All right. Now, so that works. So we meet tonight, and I either do or don't treat Taco Bell or whatever, but we decided to make the system a little more sophisticated, if you will. So, hey, what the heck? I've got a master key to all of the rooms on this floor here, so I can take over the next room also. It says instead of just room 212 where we are here, hey, what the heck? I'm going to commandeer 210 also. And all right, so its little window is either going to be on or off. Now I have 2 bits. So I can give more information. I can store in these 2 bits, and I can convey to you guys standing across the park there the answer to 2 yes/no questions. So, you know, let's go and draw some stuff out here, I guess, before we go on. So with a single bit, all right. So with 1 bit, the possibilities are either 0 or 1. 2 possible, in other words. With 2 bits, all right, with 2 bits, so I got 2 lights. Well, I might have both of the lights off. I might have the right-hand light on, but the left-hand light still off. I might have the left-hand classroom light on and the second one off, or I might have them both on. Okay. So with 2 bits, I have 4 possible values. And let's do one more then here and kind of detail like we're talking about here then. All right, and then we're going to come back and examine this a little more and draw some conclusions from that. Hey, all right, so anyway, with the 2 windows then, we can be a little more sophisticated. Instead of just, am I buying at Taco Bell? Well, I could say, okay, the first window indicates whether I'm buying burritos, and the second window indicates whether I'm buying soft drinks. And so we have 4 different combinations of I'm buying nothing, I'm just buying soft drinks, I'm just buying burritos, or I'm buying both. All right, so all of a sudden, more possible values could be represented with 2 bits. And notice that we doubled. We went from 2 possibilities with a single bit, and then we doubled. Now we're at 4 possibilities. So my question for you guys is, hey, what's going to happen if I take over room 208 also? A 3rd window, if you will, a 3rd bit that's either going to be on or off. So with 3 bits, and you know, again, we could talk about particular menu items. Okay, this is burritos, this is soft drinks, and this is cinnamon twists for dessert. All right, so you definitely need some cinnamon twists to go with your pet. That's right, at Taco Bell, no Coke, Pepsi, if I remember correctly. That's right. So we got 3 bits. So how many possibilities are there now? Well, let's kind of draw them out. All right, so this is burritos, Cokes, and cinnamon twists. None of the above. All right, 0, 0, 1, 0. Go away over there. All right, I tell you what, I want to line these up and draw them out a little neater here. So let me zap that last one there at least. Okay, so how about now? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. We're working on it here. A lot more possibilities. We're getting close to the end. And then 1, 1, 0, and 1, 1, 1. Those are all the possibilities. So my question for you guys, how many of those are there? 8. That's a funny coincidence. All right. So now there are 8 that are possible. Okay, 8 are possible. So with 1 bit, two values can be represented. With 2 bits, we jump to 4. With 3 bits, we jump to 8. What's your guess if we have 4 bits? How many? Hey, very good. So they're all powers of 2. That's exactly right. And in fact, when you look at the number of possible, see, check this out. The number of possible, all right, I'm going to take the base. We're talking about binary, so the base is 2. And I'm going to apply the number of bits as an exponent. 2 to the first is equal to 2. Oh, yeah. 2 are possible. So I take the base and apply the number of bits as an exponent is equal to 4. Oh, isn't that neat? 4 are possible. And same thing over here. You take the base, we're talking about binary numbers here, so we take the base, there were 3 bits, 2 cubed is equal to 8, and sure enough, 8 are possible. So that's kind of cool. So I want to talk more about these numbers here. I want to talk more about all these combinations that I've drawn out here. Tell you what I'm going to do just real quick. I'm going to move this down just a skosh, all right, because it's kind of cluttering that up a little. Okay, so that's a little better. All right, so let's talk more about these 8 possibilities here, and how did I come up with this exact sequence? Ultimately, I'm going to end up, in fact, I'll go ahead and do it now. I'm going to end up erasing this and this. I'm going to come back and write some more stuff over to the side. I'll tell you what I'll do. I'll just leave it and I'll write it to the left. It'll be fine. Okay, so I'm going to switch colors here. So let's talk a little bit more about 3-digit binary numbers or 3-digit numbers in general and what they mean and so on. So I'll tell you what, for now I'll switch to dark blue. So let's talk about this particular number. Let me get my pen selected. There's that. Okay. So 1, 0, 1. So when I look at this number and think about where have I ever seen this number in the popular culture, especially hint for children, and I remember as a kid, I think it was a Disney movie, and this number was in the title, and it had to do with a bunch of puppies that were born to a couple of Dalmatians. All right, this many Dalmatians. Of course, the title of the movie was 101 Dalmatians. And I do remember as a kid thinking, that's a lot of puppies. That's a lot of puppies. And to be honest, I don't remember the details of how they explained that, where they ended up with 101 puppies. Were they adopted? What was the deal? I don't even remember. Some of you guys might know, but thinking back on it, I do remember that seemed like an awful lot of puppies, especially if it was just a single litter for Pongo and, I don't remember her name. Pongo was, I think, the father. Lucky was one of the little pups. I don't remember the female puppy's name, or female dog's name. But anyway, so I finally figured this out years later. Well, they called it 101, but ultimately, if we just write it out as a number here, this being a base 10 number doesn't make sense, And let's just kind of review some stuff here. Oh, just for grins, I'll switch colors here. So we would call this here the ones position, and this is the tens position, and this is the hundreds position. And so ones, tens, hundreds, thousands, those are all powers of 10. So if we call this a decimal number, if we call it a base 10 number, then 10 to the 0. Well, any real number, 0 applied to any real number by definition is a 1. So this is the ones position. Where do these positions come from? We take that base, 10 to the first, that's the tens position. And over here, 10 squared, that's the hundreds position. So this here tells us that we have 1 100 plus 0 tens plus 1 ones for a total of 101. And again, that's an awful lot of puppies. But if we instead simply say, oh, that is not a base 10 number, it's not a decimal number, it's a binary number. So if it's binary, then well, this here is 2 to the 0. Now that's still a 1, this is still the ones position, but this is 2 to the first, this is the twos position, and this over here is going to be 2 squared, this is going to be the fours position. And now, okay, so now my question for you is, hey, now that we look at this number here, and we interpret it as a binary number instead of a decimal base 10 number, now we get a more reasonable number of puppies. So my question for you guys, on 1 or 2 hands, hold up the appropriate number of fingers to tell me what quantity of puppies were born if this 101 is interpreted as a binary number. Okay, very good, Claire. Some folks are reluctantly, if this was base 10, this would be a 1 100 plus 0 tens plus 1 1. But since it's binary, this is a 1 4 plus no twos plus 1 1. 4 plus 1. So there we go, holding up one hand with all the fingers on it. Hey, very good. So, it all makes sense. It all makes sense. It must have been that Disney movie. They called it 101. That was a mess up there in promotion of the video, or the movie or whatever. But I think that for whatever reason they wrote this quantity out in binary for some reason. It's just representing 5 puppies. That makes more sense. Okay, so with that in mind, now we know how to read a binary number and write down its decimal equivalent. So to do that, we're going to write our little cheat notes. This is the 4's position, the 2's position, and the 1's position. All right, dear students. So this here is 0 4's plus 0 2's plus 0 1's. Well, that's the decimal number 0. 0 4's plus 0 2's plus 1 1. Oh, that's the decimal number 1. All right, what is this number here? 0 4's plus 1 2 plus 0 1 2. And this is 2 plus 1 is 3. 4 plus 0 is 4. 4 plus no 2's plus 1, that's a 5. 4 plus 2 is 6. 4 plus 2 plus 1 is 7. So anyway, so when I wrote out these digits here, it wasn't just randomly figuring out different combinations of zeros and ones. Instead, I just wrote down the numbers 0 through 7 in binary, and hey, there we go. So kind of cool. All right, so with 3 bits, we can represent 8 different quantities. And all right, but real computer memory. Now we do play around sometimes with individual bits. You can store a binary quantity, just a single binary, the answer to a binary kind of question with a single bit. But for integers, we're going to deal with 8-bit integers and 16-bit integers and 32-bit integers and 64-bit integers. And let's talk about those in some detail. So we'll switch colors back over here to this. So how about, okay. Oh, that's right. One other thing to do when we're done. Let's see. So 2 to the, let's write these down here. So 2 to the first, that's 2. So with a single bit, 2 possible. And then we've done these before. 2 squared is 4 possible. And 2 cubed is 8. All right. So my question is, we'll just jump up. So a byte, in fact, we put that in our notes. A byte is 2 to the 8th. And so we could plug it in on a calculator any number of different ways, or we could just kind of do it in our head. All right, so a single bit, that's going to give us 2, and then I'm counting on my fingers. And then 4, 8, 16, 32, 64, 128, 256 equals 256. I'll show you this a different way that we can, 256 possible values. I'll show you a couple of ways we can pull that up. Of course, I can come down here and type in calc, and it'll pull up a calculator, which would work. Also, here on Unix and Linux, there's a built-in calculator on it I can use here from the old command line, and it's called BC for binary calculator. You can put that on your little quick reference or whatever then if you want in your notes. BC. And so when I invoke BC, now I'm inside of that program, and it will just evaluate expressions for me. So I could do things such as 2 plus 3 and hit enter, boom, and it spits out the answer of 5. And it understands parentheses and so on, so I could say, for instance, 2 plus 3, and then multiplied times 4. So 2 plus 3 is going to be 5 times 4. Hey, it's 20, so it works just fine. And so you have to use a star for multiplication. You can't use an X, or you can't just use parentheses and so on like you can in math class, So this kind of reflects, the syntax is kind of similar to common programming languages. And anyway, so I could, in fact, multiply 2 times 2 times 2 times 2. There's 4, 5, 6, 7, 8. There's 8 2's multiplied together, if I count those right. Hey, which is 256. 2 repeated as a factor 8 times gives us 256. We see that over here also. And then in BC, there's also an exponentiation operator. So we could say 2 to the 8th. So the little up arrow, the shift 6, will give us the exact same answer then. So, all right, so that's kind of cool. So an 8-bit integer. Oh yeah, back to our notes we go. So back to our notes, and I'll put these under memory definitions here. How about byte? We talked earlier, we're going to talk about bits and bytes and so on. A byte is 8 bits. A byte is the smallest addressable unit of memory. So bytes have addresses. Bytes have addresses. Bits do not. So you can access individual bits within a byte. You certainly can, doing some things called bit masking and so on. But anyway, bits don't have addresses. The smallest addressable unit of memory is a byte. All right. And we can declare an integer variable that is a byte, and it's only 8 bits long. So based on our understanding over here of working through this silly little program that we talked about, or the silly little example we talked about, so hey, if I took over 8 classrooms and I had 8 windows, then I could convey 256 different combinations of I'm buying that, I'm not buying that, and so on. In fact, it's funny, I remember many years ago, Taco Bell actually had a commercial at one time where they advertised something along the lines of, there are, I don't remember exactly what the number was, like, 2,096 combinations of our ingredients that we can fix up for you. And that was a power of 2. In other words, so they can put cheese or not, and beans or not, and beef or not, and guac or not, and on and on and on and on and on. Anyway, so those are just individual little yes-no things that they could add in, and each one of those would be the equivalent of a bit, and depending on how many bits there was either 1,024 or 2,096, something else like that, is the number of unique combinations of the same old stuff that they could make you there at Taco Bell. It's kind of funny that Taco Bell was the one that came up with that. And anyway, it was a power of 2. But so interesting thing, I guess, that we ought to talk about when we're talking about Java. If we declare a variable that is a byte in Java, let me draw a little horizontal line here using my 2D shape. This will allow me to draw a better line. And I'll shift to make it straight. Looks pretty good. Okay, so this is a number line. This is a number line like for math class. And, all right. So right here, smack in the middle, is 0. And now, so we have 256 possible values. And kind of based on what we've drawn up here, you know, where we start at 0 and we go on. So we have, you know, 0 and then going on up. And over here we start at 0 and go on up and so on. You kind of think the same thing. And so if we have 256 values from a single byte, you would think that they would start here and go over to here. 256 different possible values, or maybe I'll just say values instead of possible values. 256 unique values, starting at 0. Now we said there's 256 of them. Why isn't this a 256? Because we start counting at 0. So 0 is the first one, and 1 is the second one, and 2 is the third one, and so on. So 255 is the 256th value that can be represented in a byte. But, well, in Java, they don't allow this particular range of 256 values to be represented in a single byte. I wish they did. I kind of wish they did. C, C++, yeah, you could create what's called or declare what's called an unsigned byte, and it would start at 0. But, well, James Gosling, for whatever reason, when he came up with the data types and so on he wanted to support in Java, he did the following. And that is, we're going to stop right here. Okay. So this is what James Gosling gave us. I'll correct my notes over here that I kind of butchered just a tiny bit. Oops, do this. 256. Okay, so what James Gosling gave us is 256 values, and they're kind of centered, if you will, around the origin. So it's from negative 128, that's half of 256. But my question is, on the right-hand side, does it go all the way to positive 120? I'm going to get ready to hit undo here. Does it go to positive 128? If I had 128 negative numbers and 128 positive numbers, that's 256. Oh, plus the 0 itself, now we're at 257. Nope, we don't have room for 257 values, only 256. So anyway, in Java, when you declare an integer that is a byte, then the range of numbers that could be stored in that byte go from negative 128 to positive 127. And so what if I don't need any negative numbers? Well, too bad. Too bad. In other words, you're just stuck with from 0 to 127. So that's a fairly small range of numbers. And you just have no choice in Java. There's no unsigned byte. That's what it would be called in C and C++. C and C++, the unsigned byte would give you from 0 to 255, no negative numbers. But anyway, in Java, your byte goes from negative 128 to positive 127. And anyway, that's it. That's what you're stuck with. So continuing on our discussion up here then, so an 8-bit byte gives you 256 possible values. We see that they're actually centered around the origin there. So what about 2 to the 16th? 2 bytes. All right. So now I have 2 bytes of 8 bits apiece. So I have 16 bits. So how many possible values? I'm thinking since I have twice as many bits, does that mean I can double this number here instead of 256? Is it 512? Is that right? Hey, good job. That's right. It kind of does make sense that if you have an 8-bit integer and then you double it to a 16-bit integer, you think, oh, I guess I can represent twice as much information because I have twice as many bits. But we recognize you add in one more bit, you've doubled. And then another bit, you've doubled. And another bit, and you've doubled. So no, the answer is not 512. So you double from 256 to 512 to 1024 to 2096 and 2096, is that right? 2048 and then 4096. And anyway, you go on and on and on. And finally you get to 64K, which is 65,536. 65,536, if I remember that correct. We'll check that out here real quick by using the old binary calculator. Thanks for the confirmation on that. 2 to the 16th. Oh yeah, 65,536. And we would refer to that as 64K. And to be clear, a K, what is a K? It's 1024. You know, let's just kind of go over some of those powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 1024. So 1024 is pretty close to 1,000. It's actually a little more than 1,000, but it's pretty close to 1,000. And anyway, this here, we call it, because it literally is 64 times 1024. 64 is one of our powers of 2. 1024 is one of our powers of 2. You multiply them together, you get 65,536. So I remember when I was a kid. So when I was a kid, personal computers, of course, big businesses had big mainframes and all the rest of that stuff. But in terms of PCs and game consoles and those kind of things, they were pretty limited and not so great. But I do remember when, the Commodore 64 came out. So the Commodore 64, what's the 64? 64K. Oh my goodness, had a 16-bit processor. So then it could address, without having to do funny things with software and so on, it could address 64K of memory. Anyway, for those early machines all those years ago, that was kind of a big deal, the Commodore 64, I remember when it came out. But anyway, it's been a long, long time since we had computers with 16-bit microprocessors. So, starting in the mid-'80s, something like that. And you always just double. We went from 8-bit microprocessors to 16-bit to 32-bit to 64-bit, which is where we are now. But okay, what about 2 to the 32nd? All right. So this is going to be, all right. So we're going to jump from K, we're going to fly right past meg, and we're going to end up at gig. This is 4 gig. All right, 4 gig. So we can come over here, for instance. How about 2 to the 32nd? All right. So 4 gig is approximately 4.3 billion. 4.3 billion. And 4 gig, so I remember then when 32-bit computers came out. And that was pretty cool because then again, without doing any funny software tricks and so on, you could address 4 gig of memory. In those early days, our computers did not have 4 gig of memory. And in fact, it hasn't been that long ago that 4 gig of memory would have been okay. You could still buy some cheap little Asus computer to run Linux on or something else like that, and it might have 4 gig of memory even today. So even today, it's on the small side, but it's not ridiculously small, I guess. But anyway, and then starting in the 90s, then the technology was jumping to the next generation, pretty quickly. Then we doubled again. Wow, 2 to the 64th. And I'm not even bother to write this down. Well, it is 18 quintillion. Let's look at that number over here then. So it's a much bigger number. All right. So again, to get from 4.3 billion to 18 quintillion, we're going to take this number and double it and double it and double it and double it, and we're going to double it 32 more times to go from 2 to the 32nd to 2 to the 64th. We double 2 to the 32nd 32 more times, and we end up with this number here, which is a pretty big number. All right, a pretty big number. And again, if you go through and you put your comma here and a comma here and a comma, anyway, you're going to have a comma after the 18. And kind of like right here, this 4 is the billion, in the billions position. And this over here, this 18, it's 18 quintillion is that word. That's a pretty, is that number. And that's pretty big. That's a pretty big number. And, in terms of everyday life, 4 billion is a pretty big life. In fact, for my own personal, use, even 64K is pretty big. I can take care of most of my financial assets and everything else almost with like a 16-bit computer or something else like that, because you can still get tens of thousands at least, And then, wow, you jump up to 32-bit. Now we're talking about billions. And so I remember billions. Back in my day, billion was a big number. In fact, this is the honest truth, talking about big numbers. So, yeah, literally in my day, I don't remember when the first time I even heard billion, when I was a kid. But, so billion's a pretty big number. And, of course, it has been the case for quite some time now, for all of your lives, that a 32-bit integer, unfortunately, was not big enough to store the national debt, which is what now? Somewhere, are we now north of 36 trillion, I think that it is. And a funny piece of trivia, you can read this. It's been several decades now. It's been several decades. But if you go back to like the 90s or something like that, if I remember correctly, trillion was not used very frequently. Again, I certainly didn't use it very much as a kid. A million was a big number, and billion was a ridiculously large number. And again, years ago, the national debt would have been measured in so many billions. We hadn't moved to trillion yet. But anyway, just to kind of drive that point home, that trillion is a pretty darn big number, that if you go back like 30 years, the United States and England, if I remember read correctly, they didn't even agree on what a trillion was. All right, so that term was not used very often, and they had different definitions for what a trillion actually even was. That's kind of crazy. But anyway, so 18 quintillion, that's a pretty darn big number. But, again, if we're storing the number of cells in your body, or the number of grains of sand on the beaches, or the number of stars in the heavens, well, even numbers such as this might not be big enough. And it's funny, actually in PF2, starting today, we're going to be talking about our next lab, which is going to allow us to do arithmetic on numbers that are too big to be represented in a 64-bit integer. Numbers that are bigger than this over here. And there's an expression, I'll remind you of that at this point next semester. There's a little expression that computer programmers use, which is, well, if a number is too big for the hardware to store and do arithmetic on it and so on, well, the solution then falls back to software. So the silly little expression, which I've heard a number of times, is if you can't do it in hardware, you can do it in software. And the honest truth is, almost all of the things that impress you about computers are thanks to software, not hardware. As we've talked about before, what was that number one rule to remember about computer programming, about computers? Computers are, hey, very, very good. That, yeah, they do basic arithmetic lightning fast, absolutely. But beyond that, their capabilities are extremely limited. So it's almost all software that really gives us all of the gee whiz factor, I guess, of computing. That the computers themselves, basic arithmetic operations, so on, very, very, very quickly, and little beyond that, So yeah, again, yeah, for most applications, a 64-bit integer is plenty big, but for some, absolutely not. And that means that the CPUs, the arithmetic logic unit, that is part of the central processing unit, does not have the ability to add two numbers together if they're bigger than this over here. And then you have to just figure out how to do it in software then, which is, again, what our lab is. In PF2, we're going to start talking about today. But anyway, so I think that kind of finishes up our summary of our integer data types. So we're going to then come back next class period and start declaring variables of different types and assigning the different values and looking at compiler errors and runtime errors and different things like that. But one other thing I had in my notes to talk about that I luckily did write myself a reminder on when we're exploring with our first little programs. Let me do the following here. I'm going to go ahead. Control D will get you out of a BC. I think Control C will also, if I remember correctly, but Control D is kind of a little more elegant. So let's see. I've just got the two programs, vid6b. I'm going to copy vid6b.java to vid6c.java. We won't spend but just a couple minutes on this little example. All right, vi vid6c.java. And I'm going to use the $sign. And again, I don't remember if I talked about this last lesson or not, but the $sign will move the cursor to the end of the line, but it won't put you in insert mode. So it's different from the capital A will bring you past the end of the line in insert mode. The $sign will move you to the last character in the line and not put you in insert mode. And now I'm going to type RC to replace the B with a C. And I think this will compile. We'll make sure real quick. So we'll cat vid6c.java, java c vid6c.java, and java vid6c. It does compile, run, everything's fine. And I'm going to go in and edit it one more time. And this is related to something that we were talking about earlier today. Now, to be clear, that's right. So I mentioned that our program is more readable if we put some white space between various sections and so on, do little calculations here, then we're kind of changing gears and we're doing something a little different. Put some white space in the code. But to be clear, the white space, blank lines, in other words, and even the indentation, we've agreed on my little rule here, if you would, use 4 spaces for each level of indentation. That's just for the old human eyeballs that are looking at the program, just to make it more readable. Does the compiler care about that? What was that command that we learned, that VI command that we could take and connect one line with the line below it? What was that command? Y'all remember that? We were going to join 2 lines together. Is that a good hint? Capital J, very good. So check this out. Capital J, 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 J. Okay, so we look over here. I'm on line 1. My entire program is on one line. Okay. Hey, is that very readable? I like the looks of some of the students here. Oh my goodness. So I just did capital J on line 1, and it kept reading up line 2, then line 3, then line 4, kept reading everything up until everything is on one line. Cat vid6c.java. And it's going to wrap it around, but ultimately, again, if I was to do that with a bigger screen, we would see that it's going to display a little differently with a little less word wrap necessary and so on. So my entire program fits on one line, not very readable. So the indentation, the white space, and so on is necessary. So the big question is, will this darn thing compile? Sure enough does. Isn't that something? So yeah, all of that is just to make it more readable for us. And I think that even if you guys have little experience looking at code, you kind of recognize that this looks kind of, reasonable. On the other hand, the exact same code organized like this, not so good. So we want to make our code readable so that later on, if we have to go back and make a change to it, an update, whatever, we can understand what the heck we're doing. And we'd ask that other programmers do give us that same courtesy then if we have to maintain some code that someone else has written then. All right, so not too bad of a day today. Start experimenting with, we've written our small little Hello World program, but you guys can hang on till the end of your careers, I guess, and played around with PrintLine. And then also now starting to talk about different data types, and we'll go over those in more detail then. We've covered 8-bit and 16-bit and 32-bit and 64-bit. We'll give you the actual, the name for each of those then when we come back next class period to start writing more code to play around with these variables of these data types then. All right, my friends, no other homework then for today. So you guys head for the hills, and we will see you at next class period then. We'll pick up where we left off.